Now we're going to look at the potential energy due to point charges, where the force between the particles is no longer constant, but it's going to be varying. And the mathematical technique and structure that we are going to use mirrors the gravity case. So as it shows here, we're going to kind of match up the gravity case to the electrostatic case. And to just remind you what we did back in mechanics with universal gravitation, we took a particle m off at infinity and we pulled it in. So we brought it in, a displacement ds, and we calculated the work done, and then set the delta U equals negative the work done by the field, and I'll go through the mathematical structure in detail for you for the electrostatics case, but to remind you of our result, because of course mathematically we're going to get this same structure in our result, our potential energy function, if you recall, for gravity looked like this. So our maximum potential energy was actually 0 joules, right? So that was our max. And the 1 on R looks like that. So it asymptotically approached our max, and our 0 joule max is fine because we're decreasing potential energy, even though they're all negative. Our maximum value is 0, and we're decreasing potential energy when we move down and increasing when we go up. Well, we're going to do the same type of mathematical analysis for the electrostatic case, and to remind you of something really important is the fact that the m's were always positive for gravity. There was no negative m that we ever put in. And for the electrostatic case, we're going to put it in at the bottom, but let's just also get it in here. So it's because it's so important that you must have the plus and minus now into the equation for our potential energy function for electrostatics, K, Q1, negative K, Q1, Q2 on R. But let's see how that result is achieved. Well, we're first going to calculate the work done by the field as we again bring a particle, in this case a positive Q, in from infinity. So our ds is our general displacement. So our ds vector is inward. Our electrostatic force, in this case I'm using 2 positives to illustrate the derivation of the equation, is then outward. So we get a cosine of 180 between the 2 vectors. So our dot product gives us that cosine, right, of 180. Match our colors here. So our ds in polar coordinates becomes negative dr, so it's radially inward. So even though the magnitude of the vector ds is, of course, just ds itself, in polar coordinates we have to change it to a negative dr. So we do have to be careful with our positives and negatives. The magnitude of the force K, Q1, Q2 over R squared. So we factor out everything that is constant, so that K, capital Q, little q, all comes out. That's not changing in the problem. We get a 1 on R squared dr, so there's our integrate increase, R to the minus 1, right, over minus 1. And when we evaluate it, final, right, minus initial, we get our result that we recognize the mathematics of from mechanics. 1 on infinity gives us 0. Change in potential energy by definition equals negative the work done. And if we were careful with our negatives, we could account for all of them, right? This negative, black negative, would be the black negative out here, and the blue negative here is the blue negative here. So we get delta U equals K, Q1, Q2 on R. Then the function we pick out as one of those, and U as a function of R then equals negative K, Q1, Q2, as it shows here in your notes, divided by R. And of course, we have to put in the positive and the negative. So for the Q1 and the Q2. And to just kind of complete this thought for what you will be doing to apply this to problem solve, this U of R equation will give us, right, will give the initial and final joule value, right, for you to calculate delta U when you problem solve. So get that into your notes so that you know that's how you will be applying this equation. So whether they're positive or negative won't matter. You just calculate them as joule values, right? Could be positive, could be negative, depending on the Q's that you're plugging in. You'll get an initial and a final. You'll calculate the delta U, and then, of course, delta U, right? The change in the potential energy in mechanics always equals negative the change in the kinetic energy. So any potential energy lost becomes kinetic energy gained. So let me zoom back out here, leave the notes for you to pause the video if you wish to copy down what you need to know. The derivation you will not have to know as a proof. The result we will have to be very comfortable with in applying for doing our problem solving.